This is a 6, soon to be 7-axis industrial robot that I've been building as a series on my channel. And right over here is the part that we're going to be making today. This is a 3D printed prototype which I'm using to test out the fit, form, and function of my design. So far I've discovered a few minor changes I want to make. That's also a 3D printed part. This is a pretty challenging part for a beginner machinist like myself. It's got a requirement for perpendicularity between this face and this face. It's going to be machined on 4 sides, got tapped holes over here, some bearing fits on this side. So I felt like this is a good opportunity for me to walk you through the entire process of how I'm going to make this part. This is by no means meant to be a complete tutorial though. I'm a beginner machinist myself, and there's a lot I still don't know. What I do know is, as a beginner, it would have been really helpful for me to see all of the steps involved in the process. I didn't realize how many steps there were between my CAD model, then going to CAM, post-processing, work holding. I also know that many of you do this for a living, and when you stop snickering, you can scroll down to the comment section and leave us some tips and tricks on how you might make a complicated piece like this. So let's go take a look at the CAD model and we'll start there. Here's the whole assembly, and as you can see, this is axis number 7 that I referred to earlier. Although this track is really just a placeholder, my plan is to make a modular design that will allow me to latch the pieces together. Then I can essentially make the same box over and over again and extend the track as long as I want. The part that we're interested in is right here though. I've already made the changes that I wanted to make, most of the changes being related to assembly. I was having a difficult time fastening these last 3 fasteners up here. I also noticed that down in this corner, it was a little bit snug on the 3D print, but of course there'll be a weld there in the real design, so I wanted to be sure that there was plenty of room, even if the weld was a little bit oversized. So let's talk about machining this piece. As I mentioned earlier, these 2 faces need to be perpendicular, and that's because this drive gear and this axis need to be perpendicular to each other. If they are not perpendicular, let's say for example that this ends up being at a slight angle and the head is up here, then when I run my calculations for figuring out where the end of the arm is, the computer will think that the arm is here when in reality it's over here. There are 2 tapped holes here and here on both sides, and that is for mounting limit switches like this one. There's some additional tapped holes on each side as well. Those holes will accommodate a cover plate, which is going to go over this entire assembly here. So at this point, we've got at least 4 faces to machine, but in reality, I'd like to machine this face as well. But there's a couple of problems. First, I've got these arms in the way. That's not a permanent obstacle. I mean, I could either machine this face before I weld those on, but a better option would just be to machine the area under this plate, because that's the only area that's important to me. I just need to be sure that when working through my cam, I create a void areas around these brackets to keep the tool from running into those columns. The more difficult problem is this height. From here to here is almost 5 inches. Actually, it's a tiny bit over 5 inches. And because of the width of my spindle, there's no way I can get the head of the spindle down in here and still be able to machine past this face. That means I'm going to have the tool stick out 5 inches or more in order to machine this face. That creates all kinds of other problems, like the end of the tool vibrating. Actually, it just dawned on me that I bet a fly cutter will work for this. I've never actually used one before, and I don't have one on hand, so I'd have to order one. I won't have the tool in time to show it in this video, but I think as long as I adjust it out wider than the head of the spindle, then I can get the head in there and just jog up relatively close to that back until I can shave the whole area I need to reach. I wouldn't dare try to program it that way. I think I'll just jog it in there manually. But I feel like we have a solution now. Let's make the part, and then probably off camera I'll come back and fly cut that last surface. There are actually several reasons why I like welding these legs on first. And the first one has to do with work holding. If you look at this other part, which is a part that I made just prior to this one, I tried it that way. I tried not welding these legs on because I thought these narrow edges were a little bit too small to clamp on, and it would give me a chance to put a clamp right in this corner and down here at the bottom. So that's what I did. Clamped it here and here, and I stacked up some 1, 2, 3 blocks and tried to support this edge as I machined it. But I just wasn't satisfied with the results. I definitely underestimated the power of trying to cut away material out here with this cantilevered beam, if you will, sticking out. Even though this is 19 millimeters thick or 3/4 of an inch, it still flexed a little bit, and that was a problem. However, if I had had this support in place, especially in this orientation, as you can see, the beam end is much shorter, and thus you're going to have a lot less flex here. Learning from that experience, I brought these brackets out closer to the end, and I cut out this section. The material in this area is doing hardly any work at all. It's the material out here near the ends that's doing all the labor. So let's get rid of this stuff, save a few ounces of weight, and now I can still stick a clamp in this area and down here, and I've got support very close to the end. So that's reason number one. Reason number two is if you weld these on after, you're adding heat to the part, and with aluminum being a heat sink, that heat is going to disperse quickly into this part and possibly distort my machined faces. I want to pause here for a moment and put a little bit more emphasis on work holding, because to me, figuring out where to reference the part before you start cutting it, and also how to hold on to the part as you cut away material, is probably the two most important decisions that you'll make while machining the part. And yet there are hardly any videos on it and very few articles written about it. When I first started designing this part that we're talking about today, I ordered this piece of aluminum. And at that point I had only machined a couple of parts. And so this is just barely wider than the part that I needed. In my mind, I was thinking I'll machine off, maybe 20 thousandths of an inch and then start adding the features into it. But I can tell you this angle iron and none of the angle irons I bought after it are actually at 90 degrees. I need to machine off more than that, which means I should be starting with more material here. And also, how do you hold on to it? This is definitely one of the aspects of machining that I underestimated before I started. Specifically, I'm referring to how much stock material you should have to start with in order to make sure you can get the final product that you want out of it. Now that we have an idea of what we want to do, let's go ahead and switch over to CAM. So in SolidWorks, that's this tab. I also went ahead and saved this body as a separate part and did the machining for that separately so that SolidWorks doesn't think that this would be in the way while I'm machining that. For the first couple of parts that I tried to machine, I basically used the feature called Extract Machinable Features. It's right here in SolidWorks, and when you click it, basically what it does is it goes through the entire model and tries to figure out where it should drill holes, what faces it should machine off in order to give you the final part that you want. And this works okay. It's decent. You can see it's trying to machine that face, so that's good. That's not quite so good. It thinks that it needs to contour all the way down to here. The problem I have with this method is when I have an issue at the machine, for example, it does something I didn't expect it to do, I can't read the code and I don't understand why it's doing the thing that it's doing. Reading G-code is like reading an entirely different language. So I decided I really needed to select all the features carefully myself, and I also needed to be able to read at least a little bit of G-code. So here's how I decided to solve that problem. Again, this is not for everyone. It's definitely harder this way. But I decided to go through and make each feature painstakingly on my own instead of using the extract machinable features. That way I was forcing myself to really understand what everything does. And I also made myself some G-code flashcards. I used a little phone app, and throughout the day I would just flip through them. On one side of the card it would say, what is M03? Flip it over, spindle forward. Now when the machine does something I don't expect, I can go, oh, it's because I'm telling it to go to some coordinate that I didn't want it to go to. Or I'm missing a tool change, which is something that's happened to me on more than one occasion. It's not for everybody, but it helped me learn much faster. So at this point, we've automatically generated all of our features that we're gonna be machining out. I would hit Simulate Toolpath and watch it cut out the part. You definitely wanna preview everything before you go out to the machine and crash your machine. Let me tell you, if you are a beginner, like I am, even professionals actually, you are going to crash your machine eventually. You have to mentally prepare yourself for the fact that you're going to break a tool eventually. It's gonna happen. If you always have that in the back of your mind that this next tool run, I could break the tool, it'll make you a little bit more cautious, and you'll double check whether you've set your Z height correctly and whether your coordinate is in the right place. All right, let's run our simulation. All right, so we all saw that there were some problems with that code there, but we're gonna act like everything was great for a moment. At this point, we're ready to create what's called G-code. G-code is basically all the coordinates that you're gonna move the tool to and the instructions for turning the tool on and off, and even things like turning the coolant on and off. Each machine speaks its own version of G-code, so you need something called the post-processor. If you think of G-code as sort of the master language, each machine has its own dialect. You might even say that each machine has a few slang words that other machines don't recognize, so you need to translate your G-code into G-code that that machine can read. Before I hit post-process, which is already set up to go to my Bridgeport, I want to show you what the options look like. So I'm going to go on the machine and hit edit definition. Of course, if you're using a different CAM package, this is going to be in a different place, but it's all the same stuff. And then I'm under the post-processor tab, and you can see there's a whole bunch of options. Everything from a tutorial version, which is kind of a generic G-code export. There are other brand names here that already have post-processors written for them. But the most important thing, there's a Haas VF3. Be nice to have one of those in the shop. Here's the deal. In order to get my CAM package to talk to a Haas machine, I'm going to use this post-processor to make those minor translation changes from the standard G-code to the G-code that the machine can read. And that's what this does. I've already selected my G-code, so I'm going to hit post-process. I'll give it a name. This is just sample code. Hit save. And in SolidWorks, I get one more pop-up. If I try to close it right now, I haven't generated any G-code yet. So let's hit the fast forward button. And once that bar fills up, I can hit the checkbox and the code's been created. And here's a preview of the code. Let's zoom in. And looking at this, you can see it's just a long series of numbers and letters. And the first time you see this, it just looks like another language, right? What does it mean? But it does mean something to the machine. For example, I can see that I have T15M06. That tells the machine that we're going to do a tool change to tool number 15. S3094 means that the spindle speed is 3000 RPM, and M03 tells it to turn the spindle on going forward. G54 is the work offset. That's something you're going to set at the machine to determine where the X, Y, and Z coordinates are. I could go on and on because I memorized these. It's not magic, it's just something that I took the time to learn. That all of this is attainable, it just takes a while. You have to take the time to learn it, but you can learn it. This is what I would open on the machine. So we're done at the computer. I have saved this file. Let's go outside and get ready to start making some parts. Another thing I didn't think I would spend so much time doing is trying to clean the chips off of the work surface, off the vise. But even if you have just the tiniest little chip in there, it can cause a problem. I have experienced that the hard way enough times to know you have to really clean the vise and clean the bed that's being used to reference the vise. First, I'll get the vise set up, then I'll go and set my work offset. We'll talk more about aligning the vise in just a moment. Man, it's just gonna barely be in there. Should have cut that a little bit longer. I think I'm about ready to go. This is my little coolant guard that I threw together because I was tired of chips and coolant being thrown on me. So this is pretty much the point where I fire up the machine and hold on to the E-stop for dear life. And I listen to music. I always start the machine with the speed turned down, and as I see things running as I expect, I go ahead and speed it back up. All right, good first run. So I'll take this over to the bandsaw, cut off the extra, and then I can stick this back in the vise and machine off the back face. Here I've got some air cutting that I missed during programming, but since this part's not very large, I decided to just wait for it to run. Now we gotta get all this out of here, weld that up, clean all this, and then really get to the heart of machining. God. I can't believe we're halfway through the day and I hadn't got to the meat of it yet. So I want the back to be really snug and the front to be able to float a little bit. So I'm kind of pivoting around this first bolt here. But this one is almost pretty tight and these other three are pretty loose. Keep in mind, each tick mark is a 1/2 thousandth of an inch. We're talking about very small increments here. All right, we're down to 2/1000ths of an inch across 10 inches. That's getting within the almost don't care range, but the whole world is watching. I have to try to get it closer. Is it gonna stay? Oh no, we're at half. Come on, come on, come on, come on. Yes! 1/2 thousandths. I will take that. Take that, internet. Let's get all set up to load. Oh man, I need to go weld the angle iron. Golly, this part is so complicated. As you probably guessed, these faces are definitely 90 degrees to each other, and these are not. That's about what I expected. I've really enjoyed working with aluminum on this project and learning a little bit more about it as I go, both for its mechanical properties as well as how it welds. This is 6061 aluminum, and I've been reading up on this the same way I have been with the machining. The main thing that I've learned is that you gotta clean the material really well. It doesn't respond well to any dirt or grime or grease on the surface. Steel, you can kind of get away with that. With aluminum, you gotta clean the surface really well. The other thing I've noticed is how you have to adjust your feed rate as you go. Aluminum is a natural heat sink, and so as you're imparting heat into the part, that heat is quickly dispersing and you have to speed up your feed rate as you go. Otherwise, you start to melt through and really get this ugly weld if you don't make adjustments accordingly. Need to adjust the settings here. That's much better. Need to turn the juice up a little bit. That's the first pass on the wrong setting. And that's the right setting. Boy, what a difference that makes. I should mention, I also read that you shouldn't mix your brushes. So the brushes that I use for aluminum, I put white tape on so that I don't accidentally clean steel with it. Yeah, not as pretty as a MIG weld, but it'll sure be strong enough for my robot. I love doing this. All right, that's enough cleaning. Let's go machine this dude. The motor side of this plate is the flattest of the two, so I want to use that as my first reference surface. I'm going to take that and mount it here, and that means I'm going to be machining the mounting side first as opposed to the motor side. All right, taking off the welding suit, and let's put on our machinist hat. So this, we rest on top of this so that it's tall enough for me to machine all the way around this lip here. The final part is only about 5 inches tall, so I'm not worried about this piece flopping around. Eventually, that's just gonna fall off on the table. I just wanna make absolutely sure that this is as flat as I can make it, because I don't expect that surface to be perfect. And it is a very consistent 24 millimeters all the way across. I feel like there's probably a better way to do this. This is a good spot for one of my machinist friends to tell me what the secret is and how to clamp work sideways like this. Okay, that wasn't too bad. This is a passive probe that I've set up to work with my machine, but you could just as easily use an analog probe to find your X and Y coordinates manually. No fancy wire required. Nice. Sounded like it was chattering more than I expected. And I've had this tool work its way out on more than one occasion. I think it's an issue with this locking nut here. And over time they just wear out and don't lock as well. Okay, that feels pretty tight. Let's lower the speed a little bit and see what happens. Wow! Did you see the part actually come up? It definitely looks like it's getting deeper. Okay, so here's what I didn't consider. I set my 0 here, but this piece is not flat. What we're actually measuring is the tall side over here in this corner. This is where I should have set my Z. Golly. I mean, look how deep that is in the part now. That is insane. And this is why you keep your hand on the E-stop. I'm gonna find the high spot, set my Z, and get all this reset up. But now I need to reclamp this surface, and I need to check and make sure I didn't move this as well, because that's a very good possibility now. So I moved a half a thousandths. Three-quarter-inch end mill. Hey, take a look at that. Look at the grain inside the weld. It looks like we got good penetration there, which is obviously a good thing, but more interestingly is the the texture of the material there. All right, we got 2 more faces to machine. Let's get to work. Well, I don't remember which one is next. This fancy tool is called a thread mill, and it is a fascinating topic that I can't possibly start in this video. Just know that it's worth learning how to program one of these if you don't have rigid tapping abilities on your machine. Last side coming up. I cannot believe it. We might almost be done. Well, I think we're gonna call that a finished part. Everything seems to be within tolerance. Happy with the finish. Unfortunately, that first weld produced some weld spatter there. As long as these faces are good, I'm a happy camper. That was a lot of fun. I'm glad we made it through without too much damage. Man, those threaded holes came out good too. Really happy about that. I gotta tell you, I'm pretty excited about this little hunk of aluminum I just cut out here. To think that 6 months ago I wouldn't have been able to make something like this just is astonishing to me. People invested time in writing books and creating YouTube videos that showed me how they do it, and then I was able to figure out how to do it. Speaking of being enabled, there's no way I'd be able to create a project on this kind of scale without sponsors like KiwiCo. I first learned about KiwiCo at a friend's house. Let me tell you, watching our kids play together with these boxes and assembling their kits, I knew immediately I had to have this at my house. Now for us, it's a family event, and what makes it work so well is we can order different kits to match each person's interests. We would normally order 5 kits, allowing one adult, my wife, to assist the others if they need it. But apparently we're gonna have to start ordering 6 kits.
And there's a box for each of us?
There are 5 boxes.
Oh, I'm fine being a helper. I'm a person too, and I should get a box.
Okay, we'll get you a box. One of the most important features is that everything is in the box. If you need a tool or batteries, all of it's inside of the box. We always have a lot of fun, but this last time turned into an all-out tournament.
Who wants to dare race the gecko?
All right, we got the same,
Yep, they're the same.
Go, 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 go.
Oh boy.
Wow.
Oh, man, I got a long way to go.
But the sloth was winning. I want to try.
2, 1, go! 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 Go, Sloth! Oh, he's still going though. Oh, all right, that's good. I think that counts. Oh, I got 2. Oh, 3. But seriously though, it's more than just having fun with the kids. All of these crates are related to STEAM concepts. One of my lifelong, all-time goals is to inspire my kids to be able to create things using their imagination. Playing with those robots when they're small is how you grow up to make robots like this. So here's the deal. You can inspire your kids to be the next generation of innovators, and you can also support this YouTube channel by going to kiwico.com/fielding50. Go to kiwico.com/fielding50 and get 50% off of your first month's subscription. I'm telling you, it's one of the best things we ever had delivered to the house. Trying to build an industrial robot is by far one of the most epic challenges I've ever taken on, and you just dropped in the middle of the series about it. If you want to see more content like this, you should hit the subscribe button because I've got a whole lot more to share and a whole lot more pain for you to experience with me. The next video will be coming out soon. Thanks for watching. Well, we have made one huge mistake. As you can see, I've got a nice big crack going across my motor now.